So today we're going to be talking about a new video being released of a star getting eaten by a supermassive black hole. Of course, this video, just like some of the other black hole content that has been released, has been enhanced with AI. But this has great implications in our understanding of black holes, because this helps us understand the process of spaghettification as well as tidal disruption events, which I will get into later. In the Sky Report, we're going to be talking about some stellar phenomena that are going to be in the night sky, Wednesday, Thursday, Friday, as usual. But we're also going to look a little bit more long-term, especially as we are on the peak of switching from summer to fall, because it's winding down. We're a week away from September, stuff like that. Finally, we're going to be talking about a discrepancy, or I guess a fallacy, if you will, in data between projections and what is observed by the James Webb Telescope regarding ancient galaxies, which reveals that right now these galaxies may not be as big as being observed. All of that and more will be coming. This is Interstellar Insights. Alright guys, so starting off, like I said earlier, we're going to be talking about this new detailed video getting released of a star eaten by a supermassive black hole. Of course, this was AI enhanced, just like every other image of a black hole, like from two to 3 years ago, has been enhanced. But before we go into that, let's talk a little bit, kind of more of the history. So, if that's been obvious, it's very dramatic and complex the way black holes consume stars, matter. It's mainly through two words that I'm going to be using a lot, which are, well, it's kind of like a stage. So the first thing that will happen to the object is what we call, and this is a real word, spaghettification. So spaghettification essentially is when an object approaches a black hole and it starts to get super stretched out like spaghetti, hence the name. And yes, it is a real word. It's not something I made up. It's not something that the International Astronomy Union has made up. This is a very real term, and it is used when talking about black holes. But as I was saying, if you have seen pictures of black holes and then there's like a little astronaut getting stretched out, like really distorted, that is essentially what spaghettification is. And then following that, it leads into the tidal disruption event. So the history basically is that tidal disruption events were initially hypothesized in the 70s and 80s by these two astronomers, this American astronomer named Jack Hills and this British astronomer, Martin Rees. And they both had very different theories about basically how a star would get destroyed by, when consumed by a black hole. So the biggest theory out of these two astronomers is Rees's theory, and Rees predicted that the debris of a star would form a swirl of matter basically around the black hole, which astronomers would call an accretion disk. And when that happens, the disk would radiate copious amounts of X-rays, which we have found to be true through observing black holes and stuff, which technically means that black holes are not completely dark and they are emitting these X-rays, which is also part of Stephen Hawking's studies of black holes, where he kind of predicted this discovery a few years prior, when he found out that black holes kind of leak X-rays behind that are, visible from telescopes and, satellites that we have. But anyways, the kind of shocker is that the tidal disruption events that lead to these accretion disks, they don't just emit X-rays. They actually emit at the visible wavelength level on the electromagnetic spectrum. So, EM spectrum. They will emit at visible wavelengths, which means that they're easily observable with, our telescopes with the James Webb, with the Chandra X-ray Observatory, stuff like that. So, yeah, and also another surprising discovery that we have observed is the difference in temperature between Reese's theory and what was initially observed. So the temperature of the surface was a mere 10,000 degrees Celsius. Now I know that living on Earth, if we were at 10,000 degrees Celsius, we'd obviously burn. I would not be talking. You would not be hearing me. But that is very low compared to what was actually predicted, because in Ree's theory about accretion disks and tidal disruption events, he predicted that the temperature of an accretion disk would be millions of degrees Celsius, of course. That would be from the matter of the accretion disk, which would mean that not only would we not be talking, but it was likely that the Earth would be in a very, very molten hot stage that would be uninhabitable and stuff. But you get the point. It's not as hot compared to what we predicted, but it's still very hot by our human standards, because it's just incomprehensible how hot that is. But anyways, I'm digressing. I'm getting a little bit off topic. There is still a mystery in all of this, in that I'm stuttering today. Astronomers and astrophysicists still don't really have a theory explaining why these X-rays and other visible waves that are on the EM spectrum are actually getting emitted in this matter. So that is one thing that is still being investigated. Many theories among astrophysicists in the community, but there's not like one single solid theory yet. But we are still, investigating that. That is the last mystery in that part, in understanding how black holes actually consume stuff, which kind of ties in to last week's episode, where I talked about the feeding cycle of a black hole, and now we're talking about the actual feeding part. But anyways, that's still a mystery. Now, we're going to get into this video a little bit. So this video was enhanced by supercomputers in Australia that have been enhancing this footage for about a year, just to make this more discernible so we can, observe more. And from this video, we have learned that from the accretion disk, that only at 1%, that's right, 1% of the star's mass actually falls into the black hole, and that generates the heat, and the rest of the matter is what forms the accretion disk that slowly gets sucked into the black hole. But 1% of the star's matter is able to generate 10,000 degrees Celsius in the black hole. That leads to the heat and however the waves are getting emitted. So yeah, that's all we have learned from this footage. It's still big because it really shows how dramatic and complex this method is, but we're still on our way to understanding how stars get consumed. And imagine the sun gets consumed, and 1% of it gets in, and then the whole earth is fried because of how hot that is. Or actually, I don't know the exact temperature of the sun, but still, that's a lot of besides heat, just EM waves that just come towards us, and it's the magnetic storms, but just amplified. But I'm getting off task. Let's move on to our next session, to the Sky Report. Alright guys, let's move into this week's Sky Report. So, not much is really happening this week, so we'll start off. Obviously, there's actually nothing major happening tonight that's noteworthy, but I will talk about what happened this morning. Mars was actually 1.5 degrees northeast of the famous Crab Nebula this morning. So, of course, for those of you that don't know about the Crab Nebula, the Crab Nebula is about 1,000 years old. It was observed when it came into supernova. I believe it was around 1056 when that observation initially happened, and since then it's been a historic supernova, as it's been the supernova has been recorded, and now we see it as a nebula. But yeah, nothing really happening this Wednesday. We're going to move on to tomorrow, Thursday the 29th, and there is some stuff going on that night. The small constellation Lacerta the Lizard will be in prime view. I'm sure most of you have never heard of this constellation. I really haven't until it appeared that it was in peak view. But anyways, Lacerta is going to be hanging above the constellations Andromeda and Pegasus in the eastern horizon, hours after sunset. Besides Lacerta being on display, there are going to be two open star clusters that are going to be in view this night: NGC 7243 and NGC 7209. So NGC 7243 will be in the northeast area of Lacerta, that same constellation I was referring to. It's going to be shining at a 6.4 magnitude, and it will span 21 arc minutes across the night sky. Arc minutes, that's the unit of measurement to kind of describe the length of objects as they appear in the night sky, but that's just me getting a little bit off topic. NGC 7209, it's a little bit confusing me because the numbers are the same, but NGC 7209 will actually be 4 degrees southeast of NGC 7243 in the night sky, but it's going to be at a slightly fainter magnitude of 7.7, and it's going to be slightly larger in the night sky. It's going to be spanning 25 arc minutes across the night sky. So that is what's going to be in the night sky on Thursday. Now, Friday, not much happening on Friday either. But in the morning, Mercury will reach a magnitude of 1 in the sky, which will occur an hour before sunrise. And talking a little bit more about Mercury, Mercury is going to be 8 degrees east, below, and to the left of the moon, which will be in a crescent, which I will talk about later. And with that being said, a trend we'll see is that Mercury is going to be brightening across the next couple of days, so you will be able to catch it later, and much brighter, and obviously much more easier to observe. So yeah, that is the night sky for this week. Nothing really happening much, but let's go and take a look at our time. So for tonight, sunset's going to be at 7:37 p.m. The moonrise, which happened earlier today, is going to be at 12:36 a.m. That was in the at the turn of the day from yesterday and today. But the moon set's going to be at 4:49 p.m. And actually, I'll get into the phase later. But reminder that these are on Eastern Standard Time. If you don't live on the East Coast, do the conversions yourself. It's not that deep. Just do it. Do it. That's all I'm going to say. Anyways, tomorrow, August 29th, sunrise is going to be at 6:25 a.m. Sunset's going to be at 7:36 p.m. Moonrise is going to be 1:36 a.m. and moonset's going to be at 5:37 p.m. Now, for Friday, August 30th, sunrise is going to be at 6:26 a.m. Sunset's going to be at 7:34 p.m. Moonrise is going to be at 7:40 a.m. and moonset is going to be at 6:15 p.m. So, yeah, and the phase, like I said earlier, it's going to be a waning crescent. Last week was the new moon, so yeah, it makes all sense in the context of time. But anyways, that's basically the sky report for this week. I will note that from the times when sunset occurs, it seems like sunset's occurring much earlier. I think a few weeks ago, a month ago, it would have been at like 8 to 9 ish. Somewhere around then would have been sunset, but it's now 7:34. And of course, with time, we're going to see it. We're going to see sunset happen earlier and earlier until the winter solstice will happen, at which point the sun will gradually stay out for longer, but like people don't notice it because winters are very short in terms of daylight. But yeah, that is the sky report. Let's go move on to the next segment. All right, guys, so let's move into our last major subject for this episode. Not subject, topic. I sound like a school teacher. But anyways, we're going to be talking about a discrepancy in data between our own projections and what has been observed on the James Webb Telescope regarding early galaxies. So we're going to give a little bit of background. Of course, the James Webb Telescope was launched in 2021. But back then, astronomers were really excited to see these big, ancient galaxies that were around when the Big Bang occurred, and they were older than you or me or this computer or this microphone or this headset that I am hearing my voice from, because they were so old and they could tell us a lot about the early universe. However, that was back in 2021, and over the course of a couple of years, So over the course of a couple of years, and then kind of leading up to now, there's been a new study that suggests that these ancient galaxies right now are not as big as they appear. So this new study is being led by students at the University of Texas at Austin, and this study is showing that black holes in the middle of these galaxies, that's kind of a callback to last topic we were talking about before Sky Report, and then last week's topic. So I guess this episode is really just black hole theme, like black holes, and more black holes. But anyways, I'm digressing there. These black holes at the middle of these ancient galaxies add brightness to the galaxies in the night sky, which is affecting what we are seeing via the James Webb Telescope. So they've done more research into how black holes contribute brightness, because it's doing that counterintuitively, because you'd assume that they're invisible. But we talked about in the last segment how they're not invisible, and how they create accretion disks, and that's part of it. So the light is caused by friction that is created by the fast moving gas from stars that is consumed by the black hole in the accretion disk. So that, going back to the whole accretion disk concept, that accretion disk actually causes friction that contributes to brightness, because friction is heat, and so is light technically. But actually, I don't know. I have to figure that out on the theoretical physics. But anyways, I'm just getting myself confused in many circles. But that is what has been researched and discovered by these students at UT Austin, how black holes might contribute to brightness and alter our perception of these galaxies. But there is still a conflict in data, because Webb's data shows twice as many ancient galaxies compared to the projected models that we currently have. So there's multiple theories. It's still not solidified, like when we were talking about the black holes and how they're able to emit visible waves on the EM spectrum. It's like that. However, there is a little bit more of a defined theory. Of course, this theory was kind of created by and induced from the research done at UT Austin. But anyways, a theory is that galaxies back in the really olden days, back when the Big Bang was around and stuff, they were more faster and efficient at creating stars, and galaxies back then were efficient at doing that. So that led to the buildup of gas from the star formation process, and since the universe was much dense back then, there wasn't really a lot of room to expel this gas, which means that since we're still seeing light from the since we're still seeing light from these galaxies, we're still technically seeing a little bit of that light that existed from the gases that weren't able to get expelled. Because remember, light travels, I don't know exactly off the top of my head, but of course 1 light year is the amount of distance it takes for light to travel a year. Of course, these are a couple million light years away. Million, billion. The point is they're very far. So the light we're seeing is from pretty much back in the Big Bang, which means that we are seeing these gases basically clustered up in these galaxies. Since the universe was smaller back then and not as expansive as we know it today, these gases weren't able to basically get expelled by the galaxies, which is why the data from the James Webb Telescope is perceived to be twice as many ancient galaxies. But this theory suggests it has to do with the gas buildup. But the thing about this topic is it's still unknown, and there are multiple theories. So I'm actually going to briefly talk about another theory related to this. And there's a theory suggesting that the ancient galaxies are not galaxies, but that the students at UT Austin have been observing, you know it, you love it, black holes. So the reason for this is that the gas, near these galaxies has been appeared to be fast-moving hydrogen gas, which astronomers and astrophysics know is a signature of accretion disks from black holes. So once again, another mystery unsolved. These two possible theories regarding how or why James Webb is having, or we're having, this discrepancy in data between the James Webb Telescope and our projected data of ancient galaxies. So that is all for that. Hopefully someday soon we'll get some answers and have a better understanding of these early galaxies, and as well as the universe at a very early stage, right after the Big Bang. So with that being said, let's go to some astronomy trivia. Alright guys, so let's go and deal with this week's edition of astronomy trivia. Now, before we deal with this week's question, what that question is going to be, I want to talk about last week, because there seemed to be, I'm going to quickly pull up the data, but it was there's a kind of a it wasn't obviously one question that was chosen by you guys from the poll, but I believe it was, hold up, I believe it was between Jupiter and Uranus as to what the first planet to be discovered was by the telescope. And so there's kind of a rift in terms of that, but the answer was actually Uranus. And the reason why it's Uranus is while Jupiter, of course, was observed by Galileo and Huygens and a lot of astronomers in the 17th century at the time of the initial kind of invention of the telescope, especially by Galileo. The reason why is fairly simple. While at the now it's just my phone. The time before Galileo had the telescope, Jupiter was known to astronomers and astrologists at the time. It's just that it was known by different names. It wasn't universal. Today, we could, it would be known as one planet name or another. It wasn't universal, but people were able to discover, I believe it was Jupiter and Saturn by the naked eye. It just wasn't until the telescope was discovered that we could really, analyze it, of course, give it a proper name and stuff. But anyways, the first planet to be discovered was Uranus, which could not be observed by the naked eye or people had observed it and thought it was a star, which I will get to later. But anyways, William Herschel is credited as the astronomer that discovered Uranus in 1781. He initially called it the Georgium Sidus, or the Georgian star, and then eventually the Royal Society changed the name to Uranus, which if they saw the amount of jokes today, I think it would be much different. Maybe it would be like they would keep it that, or maybe they'll just call it like King George or something like that. Of course, the Georgian Sidus is obviously a reference to King George the Third, obviously during the Georgian period of British history. But anyways, yeah, William Herschel basically, because before people mistakenly just kind of ignored Uranus in the night sky and thought it was a star, but he was like the first person to see that it was a disk of like a planet and not like a dot like of stars, which led them to this discovery and led to the amount of jokes that we have. But anyways, that is last week's answer. So let's go, and I'm going to reveal the question for this week, and that question is, who discovered Pluto? That's right. I'm going to repeat that again. Who discovered Pluto? I'll put that up in a poll for you guys to take a look at after this, both on Spotify and YouTube. But yeah, that is the question, and the answer will be revealed next week. But anyways, that's astronomy trivia for this week. Let's go close out this episode. Alright guys, so thank you for listening to this week's edition of Interstellar Insights. Next week, for me at least, school starts, which means that just podcasting in general might slow down in general, but hopefully I'm able to manage school and this podcast. I'd like to still be able to keep the one episode per week kind of schedule going, churning through. And since school started, I really would love to be able to work on shorts, but I just cannot, especially with school and a bunch of other stuff that I won't get into. But, whenever I just have time or school's out, shorts would definitely be on my mind, and hopefully we can get some of that out. So yeah, next week hopefully should be regular scheduling, regular scheduled program, if you will. But yeah, if you like this episode, please feel free to like and subscribe. It really means a lot to support and grow this out, so we can, of course, improve some of the content. We can make it a little bit more entertaining, but overall keep it interesting, and of course push it, strive for that. So yeah, that is all I've got. This is Michael signing off.